And let's hope this works. So, let's start with some simple definitions. So 12.1, topic 12.1. Actually, let me just grab a different pen. Like that. Is the interaction of matter with radiation, which, as the name suggests, is how matter interacts with radiation. So, let's start by describing what photons are. Photons are a particle that carry light, and they obey a property called the wave-particle duality, which basically means that depending on the experiment, you will see it behave as a particle or as a photon. So it is both a particle and a photon. So it obeys the wave-particle duality. It behaves as both a wave and a particle. And then it's important to note that, for instance, some examples, it will behave as a wave in like refraction, right? So you will see it behave as a wave in, for example, in waves, in optics, it will behave as a wave. It also exhibits wave properties in absorption or emission spectra. However, it behaves as a particle for example, when it interacts with other matter, such as electrons in the photoelectric effect. Or in the Compton effect, which is something that it's another example of, and so it's important to note that it will behave as a wave or as a particle. You won't see it behave as a wave and a particle in the same experiment. It will always behave as one or the other, but it can behave as both. So, Einstein postulated after that the energy of a photon is quantized. Now, what does this mean? It means that it can only take integer values of, or it can only take certain discrete values, right? So so it can only take energy E, let's say 2E, 3E, right? So it can only take certain values of E. It cannot take any value in between E and 2E. That's what discrete energy means, and it's one of the main postulates of quantum mechanics. And it's actually what's called quantum mechanics, because quantum or quantized means discrete, and quantum mechanics means it can only take energy can only take discrete values, right? And obviously, this is not true. It doesn't take E, 2E, and 3E. It rather takes E equals HF, so this is what the energy is given by, right? Where H is 6.63 times 10 to the minus 34 joules per second, and it is the Planck constant. And it denotes how big a quanta of energy is, right? So an atom can only take discrete values of energy given by HF. Also, you can write this since F is equal to c over lambda, where c is the speed of light, because we're talking about light. You can write that as E is equal is equal to hc over lambda. These both mean the same thing. Right, so that's just general revision about how photons work. Now let's move on to the photoelectric effect. By the way, if I do miss something, please tell me. I'll explain it later. I did this a couple of years ago, so I may forget certain things about the syllabus and talk about others which aren't in the syllabus. So the photoelectric effect actually awarded Einstein the Nobel Prize in, I think it was 1915, but not sure. Or 1921, it was one of those 2 years. And essentially, the very, very short explanation is that it basically means that if you have a sheet of metal, say this is a sheet of metal, and you have light incident upon it, you will release electrons. Now, what's so important about this, and what made it such a discovery, is that the entire experiment is actually a bit different. I'll go into the setup in a second. But what made this so interesting is that according to classical mechanics, so let's here write classical mechanics, you have that the intensity in classical mechanics, given that it is proportional to the energy, I don't exactly remember the relation, but it is proportional to the intensity is proportional to the amplitude, which is proportional to the energy. In classical mechanics, the intensity should affect the energy of the electrons. Right, so the more intense the light is, independent of what frequency it has, the more energetic the electrons shall be. We'll get to how we measure how energetic they are in a second. But what's observed in reality is that it only affects the number of electrons released. Now, obviously, this was not expected according to the postulates of classical mechanics and classical wave theory, but it can be explained by this right here. Right, because what was observed was that the higher the frequency, so it was in classical mechanics, the frequency shouldn't have any effect whatsoever. Right? It would just, the frequency is not related to energy in classical mechanics and classical wave theory. The intensity is related to the amplitude, and the energy is related to intensity. So the frequency shouldn't have an effect. But what is observed is that the higher the frequency, the higher the energy of the electrons. In other words, E is proportional to F, where the proportionality constant is our Planck constant that we mentioned earlier, right? And so we get the relationship. So that's basically the photoelectric effect in a nutshell. I will go into a bit more detail in a second. But what we can measure, right, because electrons, what they do is carry current, what we can do is, let me just pull out a diagram in a second. Give me 1 second. So what we can do if we have an experimental setup that let's say looks something like this. So let me just quickly, well actually I don't know if I have access to that file, so I'm just going to reproduce it. So it looks something like this, and this is a class envelope, something like this. Then we have something like this here, and then we have light coming in through there. Well, okay, actually, this may not serve the purposes of what I'm trying to explain. So let's just simplify that, and let's just say we have a sheet of metal. Right, so let's say it's a sheet of metal. We have a inside a glass tube. And then here we have an anode connected to a circuit that has an ammeter. So that's going to be an ammeter, right? Again, I hope you get the idea. So very schematically, right? And this has some light incident upon it. And that's how we can measure the number of electrons, right? And let's assume, for the time being, let's assume that there's no potential difference. It's just a gap. And there is vacuum inside. And what we see is that, well, we see that there is a certain frequency, which I'm going to call F0. Should if this be right, that would be great. So we observe at a certain frequency F0, no current is measured. So basically there's no electrons bridging the gap. What does this mean? It means, well, there is a cutoff frequency under which we don't have enough energy to release the electrons. And this doesn't make sense in the picture of classical mechanics, because in the classical mechanics, well, energy is not quantized. And sorry. And so we see this cutoff frequency. If we plot a graph of, say, current, actually I think that's not current, it shouldn't be current, it should be energy, my bad. If we plot the energy against the frequency, we observe that it has a slope that looks like this. This slope is going to be given by h, right? Because it's our proportionality constant, it's a linear relationship. And that it will cut this axis at F0, which is our energy, our cutoff frequency, under which we observe no release, no current. And then it will cut the y-axis in what we call psi, or the work function. What the hell? That's supposed to be an arrow. Which is the minimum energy needed to rip out an electron from the metal. Now, what happens if we actually put a voltage here? Let's say we have a potential difference of 5 volts. Well, what will happen is the electron needs the energy to be ripped out of the metal given by the work function, right? And it will then need 5 electron volts of energy to cover, right? Because an electron volt is the energy needed by an electron. to overcome a potential difference of 1 volt. And so that's 1 electron volt. And so if you have a potential difference of 5 electron volts, what you see is that, well, you need 5 electron volts of potential. Now, there is an interesting thing that happens. So if we plot, say, voltage against current, I actually don't know if this is in the syllabus, so maybe it isn't. But if we plot voltage against current, what we observe is that we get curves that look like this, right? So there is a saturation current, which I'll talk about in a second. And let's say this is our current IB, and this is our current IA. And what we see is that it starts dropping down, like sort of like this, right? Sort of like that, and then reaches that saturation current again. And it always drops to that same frequency V0. Which means that the photons have some energy, and so they can overcome. So this is obviously positive, and this is negative. So if you add a negative potential difference, so basically you're bringing electrons towards, right? So a negative potential difference means you're attracting electrons towards the sheet of metal. You still have some electrons that make it through, because those get enough energy to overcome the potential difference, aside from making it outside of the work function of the sheet of metal. And then others just get stuck in the middle and then get pulled back. Are there any questions so far regarding this? No questions? Okay, so so the saturation frequency, or the saturation current here, right? This you can try to tell me when it happens. It should be pretty straightforward. When do you think we reach this current right here, after which, even if we increase the voltage or if we increase the frequency, we observe that there is no more, that we don't observe a higher current? And why would you say that's the reason? Anyone want to take a guess? Okay, well, so essentially what happened, right? At one point, you have all the electrons make it to the other side of the potential difference, right? Because like when you have a positive potential difference, you're pulling electrons that way. So you're pulling them towards the anode, right? And at one point, you have all the photoelectrons make it to the anode. And so since the current is proportional to the number of electrons, if all the electrons make it, then you don't. So this is for a given frequency, by the way. And so since it's proportional to the number of electrons, once all the electrons make it, you're not going to measure more current, because you're not going to get more electrons to bridge the gap, right? So at this point, you already get all the electrons passed. And so you get a higher current. Or you just saturate the current. You won't get any more current. Now, I actually don't know if I'm going outside of the syllabus. If you guys don't do this, I apologize. I am going off my lecture notes, but I could have sworn that this in IB. So what you can know is that the energy. Energy of the fastest photoelectron, or the fastest electron that makes it through, right, is basically going to be given by K max is equal to the energy of that, to that electron, V0, in electron volts, right? So V0 is the cutoff frequency after which we don't measure any. Is it lagging? Oh, did I? Is it working? Oh. I mean, my internet connection is pretty shit, so it could be that. I really hope. Yes, it will be recorded and sent to you. Okay, so anyway, just last thing I'm going to mention. I'm not going to go too much into detail anymore, but like the kinetic energy of the fastest photoelectron is going to be given by that cutoff frequency. Because that cutoff voltage, right? After that point, we don't measure any energy. So the maximum energy an electron can have, or the the energy of the fastest electron, photoelectron, is going to be given by EV naught. And as you see in this image, it is independent of the intensity of light. It is only dependent on frequency. So A is one frequency. I did make a mistake. There's not for a given frequency. So A is frequency 1, and B is frequency 2. I did. That's why you labeled your figures. I did forget to do that in my notes. But so A is frequency 1, B is frequency 2. We can see that depending on the frequency, we get a higher energy, right? We get a higher intensity or higher energy, because intensity is a measure of energy. But the minimum energy you need to bridge the gap is still the same, independent of your frequency and independent of your intensity, especially. Actually, did I? No, wait, fuck up. Shit. No, shit, no, my bad. IA is one intensity, IB is another intensity. Actually, there's not going to be an exam, so forget about it anyway. But IA is one intensity, so what we see is that the higher the intensity, that's it. The higher the intensity, the more electrons that make it through. So that the more current you measure, but the minimum frequency, the minimum voltage is still the same for a given frequency. But the lower the intensity, the less electrons that make it through, and therefore the lesser the current you measure, because there's less electrons. I'm sorry for that, but anyway, this is not going to be the exam. It's just an extra, but it does help you understand the photoelectric effect better. So basically, just remember, intensity only affects the number of electrons released, and frequency affects the energy of the electrons, and therefore the higher the frequency, the bigger the potential difference you can bridge, and the higher the intensity, the more current you will measure. But if you increase the voltage, right, if you turn that knob up, let's say, and increase the voltage to, say, minus 6 volts, so you have a negative potential difference and you're pulling an electron back, you can increase the intensity all you want. If you're not measuring a current at minus 6 volts for, let's say, 30 watts of intensity, you're not going to measure it for 1,000,000 watts of intensity. However, as soon as you make it to that cutoff frequency, so frequency affects the energy of the electrons. So basically, that means the frequency of the energy of the electrons. That means the more energetic an electron is, the bigger the gap it can bridge. Right. Going back to here. If you have a negative potential difference, the bigger the electron, or the higher the frequency of the light, the greater this potential difference can be before an electron actually doesn't have enough energy to make it to the other side. Whereas intensity just affects the number of released electrons. So the more intensity, the more electrons you have released, and the more frequency, the more energetic those electrons are. That's the really short summary. So intensity basically is a measure of the number of photons. Actually, measure of number of photons, my bad. Whereas frequency is proportional to the energy of a photon. So you can think about it as the more intense the light is, well, you can actually, so let's say this is a lamp. The more intense, the more photons you will measure coming out of that lamp, right? There's more photons coming out of it. And since electrons are just in a sheet of metal kind of distributed like this, let's say that we're only talking about the outer layer, the more intense the light is, the more interactions you will get between photons and electrons, And since all those electrons have the same energy, because the light has the same frequency, you will rip out more electrons from the sheet of metal. And the more frequency you have, the more energy you will give those electrons, right? Subtracting from the work function. The kinetic energy that an electron has after interacting is going to be HF minus the work function, because the work function is the energy you need to rip it outside of the metal, of the sheet of metal. And HF is the energy it has from the lamp that we're using, right? So the energy it has to bridge the gap is just going to be given by HF minus phi, where phi is the work function. Now, I have a question, an interesting question. I don't. Some of you may be able to answer it. It's just more of a conceptual understanding. Why do you think that the photoelectric effect only happens with metals? Yes, exactly. So it's essentially because of that, right? You have valence electrons, you have the sea of electrons floating around the atoms, so those electrons are not very tightly bound to the nucleus they are attached to. And so they have a low work function, they don't need a lot of energy to actually be made into free electrons that you can rip out and ionize the metal. And so that's why work functions and essentially metals have low work functions. Yes, if the intensity increases, you will increase the current, because you will see because current is proportional to the number of electrons flowing past. And so the more electrons you have, the more current you have. But then again, if you increase the potential difference, independent of the intensity, there will be a point at which you measure zero current, because you don't have enough energy for any of the electrons to make it past. Does that make it clear? Okay, cool. Then there is, just as an aside, you can have things like photoelectric effects and photon interactions with matter, with elements with higher work functions that aren't metals. But these are obviously not in the syllabus. I'm not going to go into them. But if anyone wants to look into them, they are, for instance, things like the Compton effect, which I mentioned earlier. That's what happens when you have an interaction with matter, with work functions that are much higher than those of metal, right? So what happens when you interact with an atom from iron or uranium, even, right? At that point you need a lot of energy to actually rip it out because they're really tightly bound. Whereas in metals, they are free electrons floating around, and so they are easier to work with. So that's it for the photoelectric effect. I did think I went a lot into detail, more than I was hoping for and aimed for, but I hope that made it really clear for you guys. So now we move on to matter waves. So we mentioned earlier the wave-particle duality of photons, right? So basically, but now it turns out that de Broglie postulated in his PhD thesis, that everything obeys the wave-particle duality. And that the wavelength of a certain particle is given by P is equal to H lambda, which implies that lambda is equal to Hp. And this is known as the de Broglie wavelength. This is a postulate. I'm not sure if it's proven. I definitely don't know how to prove it. I don't think you would know, because if there is a way. And this is the momentum, and the H is the Planck constant. So, what does this mean? It means it's basically a huge statement about the grand symmetry of the universe. I'm not going to go into the implications of it. All you need to know is that things, very small things like electrons and protons and neutrons, things in that scale, probably more electrons. Some of you may have heard of the scattering experiment, the double slit experiment, that actually proves this. But what was what? the double slit experiment. Oh, I'm actually on, I don't know what part I'm on matter waves. The double slit experiment is the experiment where you have an electron in a box, and you have two boxes here, and you have the electron travel to, you have an emitter here which emits an electron, and here you have a sheet of detectors, or like something to detect the electron. And what you see is, if you try to measure the position of the, if you just let the experiment run and don't have an observer, you see a scattering experiment. No, it has to do with wave particle duality. It's just, I don't know if it's in the AB, but essentially what happens is you would see a diffraction pattern here if you don't observe what box the electron is in. So you would see something that looks like, I don't know, something like this. Right, so you see a diffraction pattern of something that's behaving like a wave. However, if you try to measure, before actually ejecting the electron, you actually try to measure where it's at, and you go and you measure it, and you find it's in one of the two boxes, what you will see is something that looks like this. So you will see a pattern here and a pattern here, and you won't observe the diffraction pattern. So essentially, the wave in this case, the electron in this case, is behaving as a particle, whereas when you don't observe it, it's behaving as a wave. That's the double scattering experiment. It's one of the most important experiments in quantum mechanics, because it just comes to prove this wave particle duality that we were talking about a second ago. And now I'm just going to do some calculations to give you an idea of some it's going to be some ballpark approximations. So I'm going to make some decent approximation. So let's assume that h is 7 times 10 to the minus 34 joules per second. And let's look at the mass of an electron, which I'm going to call me, as 9 times 10 to the minus 31 kilograms. And now let's calculate. Let's say that our electron is moving at velocity, I don't know, let's say 10 to the 5 meters per second. And so let's calculate its Broglie wavelength. Lambda is equal to h, which is, we said 7 times 10 to the minus 34, over 9 times 10 to the minus 31, times 10 to the 5. And if we simplify this, we get that this is roughly, that's roughly 0.8, approximately, I think. But I'm pretty sure it's like 0.77 or 0.87. We can compute it real quick. 7 over 9 is 0.8. So we can approximately say this is 10 to the minus 34 plus 10 to the 31 is 10 to the 3, or 10 to the minus 3 over 10 to, so we can basically say this is 8 times 10 to the minus 9. So it has a measurable wavelength, one we can observe in the visible, well, it would be in the visible spectrum. This is in the order of nanometers. So we can measure it, right? What happens now if we look at something moving at the speed? Let's say it's moving at 10 to the 8, which is 1/8 of the speed of 1/3 of the speed of light. Same analysis, 10 times 10 to the minus 34, 9 times 10 to the minus 31, times 10 to the 8. And so we get minus 34 plus 31, which is 3, and now we get 8 times 10 to the minus 12. This is HL. And so now we see that this is in the order of picometers. I think it's picometers. It's 0.8 picometers, which essentially is still measurable, but it's much harder to measure, right? We're not talking about classical optics anymore. We're talking about quantum optics. But now let's look at a truck. Right, so I haven't looked this up, but I'm going to say that a truck weighs around, let's say 1,000 tons. Or let's just go with a car that weighs 1 ton to make it easier. So 1,000 kilograms. So that's going to be our mass. Right, did we make the same approximation for h before? And let's say that it's moving very, very slowly. Let's say it's moving at 0.1 meters per second. Right, so it's moving terribly slowly. And we compute its de Broglie wavelength. So we see 10 times 10 to the minus 34, 10 to the 3, times 10 to the minus 1. And what we observe is that's 10 to the 33, 10 to the minus 34 plus 10 to the minus 10 to the 33, 10 to the 36, so 7 times 10 to the 30 minus 36 meters. So the wavelength here, right, the de Broglie wavelength is really, really small. Take into account, this is for an electron traveling at 1/3 of the speed of light, and it's 10 to the minus 12. Here we're talking 10 to the minus 34, which is, I think, on the order of Planck length, or even smaller than that. I'm not entirely sure of what order of magnitude Planck length is in. I think it could be 10 to the minus 34. So we can't resolve this. So we don't see this wave-particle duality in our day-to-day lives because the waves are just too small. Right, so that's basically how the wave-particle duality behaves at high energies, or at the macroscopic limit. You can compute it with lighter things. Even if you take something that's 1 kilogram, you would still get 10 to the minus 33, which is way smaller than anything we can resolve. So you get the idea. It's really small. Even if you take something that's a gram, you would still get really, really small wavelengths. Okay, so now we talk about pair production and annihilation. Pair production and annihilation. I don't think you go into much detail about this, but I'm just going to give you I'm going to go over the very basics. When a high energy photon collides with a nucleus, it's going to split into a particle-antiparticle pair. So let's say we have an electron like that, right? So that's our photon, and there's a nucleus here. There's our nucleus. Now what we can see is that this electron might split up into a particle and an antiparticle. So we will say antiparticle. For those of you familiar with Feynman diagrams, this is the notation for an antiparticle. Just an arrow traveling like backwards. And these obviously with the same angle because they both have the same mass. It's opposite charges, but and opposite quantum numbers, but same mass. Now, why does there need to be a neutron? Well, there needs to be a neutron for conservation of momentum to be obeyed, because a neutron can absorb the energy can absorb the momentum of the part of the photon, right? Because the photon has momentum, without drastically altering the energy balance. But if you look at this, what initiates pair production? It's actually spontaneous. It's just there's something that can happen in the presence of a nucleus. It needs to happen in the presence of a nucleus, though. It won't happen if you just have a free photon traveling through space. It's not going to spontaneously become a proton and a positron and an electron, for example. But since here you have all the momentum traveling that way, and here you get a perpendicular element of momentum, and which cancel out, my bad, and a parallel component of momentum. So momentum wouldn't be conserved. You just have this in free space, and because you have momentum that's traveling in the x direction, and suddenly you get momentum in the y direction, and less momentum in this direction, right? And so the overall momentum is traveling in that direction, but the momentum initially was traveling in this direction, which doesn't make any sense if you don't have a nucleus that can actually make up for that by absorbing some momentum for that change in momentum that was given. And the opposite can happen. You can have a particle and an antiparticle. Let's say we have a particle here and an antiparticle here, and they collide and they release two photons, one this way and one that way, so that momentum is conserved. And there's a couple of things to note. This particle and antiparticle pair, usually you see a positron and an electron, right? So a positron, actually that would be an electron, and this would be a positron. because they have the lowest rest mass energy, and the rest mass energy, m0 c squared, is called the rest mass energy. Is the energy an electron particle has just by staying still. It doesn't have any kinetic energy, no nothing. Just a particle standing still has a rest mass energy of m0 c squared. And since the electron is the lightest particle, you actually see that it has the smallest. Yes, I'm recording this. Nope. Yes, I am. And so since an electron has the smallest particle, you need the smallest. You need less energy in the photon to actually make it up, right? Because what you need in the photon, the energy the photon must have in order to create a particle-antiparticle pair, is at least 2m0 c squared, right? Because it needs m0 c squared for this particle, m0 c squared for this particle, and any excess energy will be given as kinetic energy. Which actually means you need a little more than 2m0 c squared, because if not, the particles will just be stationary. But you can technically, and it has been observed, you can create any particle. You can create a proton or an antiproton if the photon is energetic enough to have two times the rest mass of a proton. You could create a proton and a proton pair, or you could create a neutron to neutron pair. You can create any pair of particle-antiparticle as long as the initial photon has enough energy, right? And each of these photons, right, they will have m0 c squared energy. Because of this. Because each of these particles is m0, well, actually, they would each have 1/2 the kinetic energy of the particles, plus the rest mass energy. Right, so if this one has energy Ke, and this one has energy Ke, plus m0 c squared and plus m0 c squared, you would see that each one of these has m0 c squared plus Ke. And yeah. Okay, so now we move on to the Bohr model, which is actually one thing that I'm not extremely good at, but whatever. Bohr model. So this is a model which is actually used a lot in quantum mechanics. I learned about it. Well, anyway, it basically has to do with a quantization. So when you ask for energy of a particle, then we always add the kinetic and mass energy. If they ask for the energy of a particle, yes, unless they specify they only want kinetic energy, then you don't have to take into account the mass energy. But if they just tell you what's the energy of a particle, of an electron moving at a certain speed, I would say add the rest mass energy, because that is part of the energy. There's actually, in relativity, if you look at relativity formulas, and you look at, for example, the momentum of a relativistic particle, or you see that it is actually depends on the rest mass energy or the energy in relativity, right? As an aside, the energy in relativity is given by, if I recall correctly, it's m0 c squared to the squared plus. Actually, I don't remember. Let me just. It was momentum squared. Here we go. Plus p squared c squared. So you see, it depends on the relativistic energy, and this is just moment, and this is just kinetic energy, right? Because speed. And so yes, you need to account for the rest mass energy. Just that macroscopic, the rest mass energy is almost always 0. It doesn't really affect. Nope. God damn it. Okay, so we were talking about the Bohr model. So the Bohr model basically is about the quantization of energy, quantization of angular momentum. Can you? Why the hell is this so slow? Quantization of angular momentum. So, let's go. Okay, so basically Bohr postulated that the angular momentum of an arbitrary electron is given by mvr equals nh over 2 pi, where actually we denote h over 2 pi as h bar. And this is actually super important in quantum mechanics. It shows up everywhere in the Schrodinger equation, as I'll mention in a second. It shows up in basically everywhere. I've seen it a bunch in my condensed matter physics lectures. So it's not like some trivial constant. It's actually pretty important. Where was I? Oh yeah. And he also stated that it has kinetic energy, given by the kinetic energy of a sphere, which is ek equals mv squared over r over 2, which is equal to, we can just solve from here, n squared h squared over 8 pi squared r squared. Now, I'm not going to go into the entire solution of this. You can just solve it from here if you want to. You can just have mv, you divide both sides, like you can do it if you do mv r and divide that by 2 and equals nh over 2 pi, and you'd have to divide that by 2 as well, so you get mv r equals 2 nh over 4 pi over 2. I mean, you can do this yourself if you want. If you want to, I can post it later. Do you want me to go over derivation or not? Or is there no need? Okay, I'll go over the. Okay, sweet. So we have MVR is equal to NH over 2 pi. I don't know if it's necessary for questions. Now we can divide both sides, so let's just isolate MV here so that we have something that resembles the original equation, NH over 2 pi r. And so now we do MV over 2, we divide both sides by 2, and NH over 4 pi r. And wait a second. Did I? No, wait a second. And so now we need to do MV here. We multiply this by B and we divide that by 2, and we have NHV over. Actually, I don't know how the hell. I think you actually need to solve this Schrodinger equation to get here. I'm not sure though. Or you can square both sides and then divide both sides by m. Yeah. Okay. So if we square both sides. So we square this and we square that, we get m squared b squared over 4. Yeah, I mean, you can do it either way. I don't think it will really matter, as we'll see in a second. N squared, h squared, 16 pi squared, r squared. And now we can pass a 2 multiplying to that side, right? So we can multiply both sides by 2. 2 there, 2 there. And so this becomes a 2, and that becomes an 8. And now we divide both sides by m, and we get mv squared over 2 is equal to n squared over h squared, 8 pi squared r squared, which is the formula we're looking for. And you actually get this from solving the, I think it's actually a solution of the Schrodinger equation, if I recall correctly. But I'm not going to solve that. Because it's not in the syllabus, not even close. I learned about it this year and I'm in my second year of physics degree, so that comes to show. But anyway, what this shows is that the energy of a certain level, right, n is an integer, it basically comes to show that En, or the energy of a certain level, is minus 13.6 n squared over EV. Now, because, well, h squared is a constant, 8 is obviously a constant, pi squared is a constant. And actually, I forgot an m here, my bad. And so m is a constant, we know the mass of an electron, and r, as we just said earlier, is quantized. We can figure it out. And so that basically just gives us this solution right here, which is the quantization of energy of an electron. And I mean, that's basically all you have to do in regards of, actually, one more thing. It basically just, this means that the allowed electron orbits are those for which an integer number of electron wavelengths fit around the circumference of the orbit. So you will get basically orbits that look like a circle, or just that look like something like this. That's actually supposed to be waves, but you won't see. So you will always see that it's an integer number of wavelengths. You won't see something that like wraps around something like this, like that, right? That's not full wavelength. You won't observe that. Okay, next thing. So the next thing we're going to look at, okay, there we go. The next thing we're going to look at is the wave function, which is actually a pretty interesting thing. So there's only a couple of things you need to know about the wave function, and it's usually denoted by the Greek letter psi of xt. And it just basically gives you information about the particle. It is known as the Schrodinger equation, and I'm not going to go over it. I'm not going to go into detail about it, because there's really nothing you need to know, aside from the fact that it gives you a lot of information about a particle. It gives you the momentum, the energy, and so on. All you need to know really about it is that it's the square of the wave function is equal to the probability of finding, so evaluated between points A and B is the probability of finding it between points A and B. Now, for those of you who want a bit more detail, this is actually the product of multiplying that times its complex conjugate, because believe it or not, it's a complex function. And then you would also have to normalize it. So you want the total probability to be equal to 1 over all space, because obviously the particle exists somewhere, right? So you got to find it somewhere. And so the total probability is going to be equal to 1. If it isn't equal to 1, you have to normalize the wave function by integrating it over all space. I'll give you a question using that formula. Don't worry. You can even try to solve it here. I think it was something like that. Okay. You can. I've seen questions about it. Basically, I've seen one question about it. I think I got one in my paper. Basically, what they will give you is they will give you a function that looks something like this, right? So let's say we have the modulus of our function on the y-axis plotted against, let's just say it's a time-independent version, right? So it's not dependent on time. So it's basically just a function of position, or whether we're looking at a snapshot at a certain position, right? And you get something that looks like this, and then it's pieced like this, and then it just goes something like this. And there's a bunch of squares here, right? So it's a grid paper. It's kind of like a paper 3 question. Something like that. And there's this point, let's say A, and this is point B. and they tell you, again, this, let's say this is 1, and they tell you, okay, what's the probability of finding it between points A and B? And so you'd have to count squares, or if they give you the function, do the integral, but I doubt they do that. So just count squares, find the area under this curve between points A and B, and that would be the probability. And that's basically all they're going to ask in regards to Schrodinger equation. In my opinion, it's pointless to teach it, because there is literally, like, if you're just going to teach that. No, yeah, I've seen it asked a couple times, but yes, it's proportional to the modulus of the function, which is given by that, right? So it's the wave function times its conjugate. So that's going to be the well, it's square of the modulus, I think. Yeah, it's square of the modulus. That's the one. My bad. Yeah, so it's square of the modulus, right? Which is basically that. It's the function times its conjugate, and that is going to be equal to 1 over all space, and yada yada yada, which is exactly what I just said. But thank you for correcting me on that. But yes, you are right about that. So now I think the next thing we're going to talk about, I am going to talk about. Wait, you guys do electron in a box? Oh, that's cool. So now let's talk about quickly. Let's mention it got removed. Well, okay. So let's I was planning on going over the entire solution to the Schrodinger equation for a particle in a box in an infinite potential. Well, shame on you. I guess you miss out on that. What a shame. I'm sure you're all missing out. Anyway, let's talk about tunneling, and then I'll move on to the uncertainty principle. So tunneling is a quantum mechanical effect, because as we just mentioned earlier, right, particles in quantum mechanics are behaves as waves in particles, so they have, actually, I guess that's kind of oxymoronic, but I'm going to ignore it. So essentially, let's imagine we have a function here, right? Let's say this is v naught, and this is some potential vt which is greater than v naught, and let's say we have a wave function, right, which comes over here, right? And let's say this wave function has energy. Let's say it has energy v1. Obviously, this is greater than v1. In classical mechanics, if you impact a wall and you don't have enough energy to overcome that wall, you just get reflected, and you can't make it through the wall. However, since we were talking about here probability, right? There is actually a probability of you finding the particle on this side of the potential barrier, because since it's a probability, it's never zero, right? So there's technically a probability of you finding an electron for an atom on the other side of the universe when you actually make collapse, when you actually observe it and make it collapse. So when you actually detect the particle, you could detect it on the other side of the quantum barrier, or the potential barrier. But what you will see is, obviously, right, so you will see that the potential energy kind of decays through the potential barrier and it becomes smaller on the other side, obviously, as one would expect. You don't have the same probability of finding it before the potential barrier. And well, I mean, that's basically it. You basically have a probability of finding a particle on the other side of potential barrier, and the probability is proportional to the width. The probability of finding it here, which we'll call p, is proportional to 1 over the width of the barrier, and also proportional to the to the difference between Vt. Yes, the session will be recorded. I think I'm recording. Am I recording? If not, I'll re-record it later. Yes, I am recording. So it's proportional to, it's inversely proportional to that, right? So the more energetic this function is, right? If this function happened to be here with a potential, let's say V2 greater than Vt, at that point it would actually traverse the potential barrier without any problem, because it just has enough energy to do so. But if it doesn't, then we'll tunnel through, and the higher the potential barrier is with respect to the energy of the function, the less probability it has of making it through. That's basically where the particle in a box thing comes from. You could have like you have a particle in a box proportional proportional to the energy of the particle. Yes, so the more energetic the particle is, the more probability you have of detecting at the other side. Right, so if it has a potential energy, or an energy, forget about potential energy, just talk about energy. If it has an energy greater than the potential energy of the barrier, you will have a probability of detecting it at the other side, as if the barrier wasn't there, because it's going to make it past, right? It's basically, if I have a wall here and they toss a ball over the wall, you're going to be able to find the ball on the other side, right? But like, think about now that the ball isn't defined, and think about it in quantum terms. But basically, I'm doing the same thing. I'm throwing the ball over the wall, so I can't find it on the other side, right? If I can't throw it over the wall, now in quantum mechanical terms, I have a probability of finding it on the other side, but it's lower than just making it over the wall directly. I don't want this to confuse you. The fact that if V2 is greater than Vt, you won't always find the particle here. You could find it here as well, but the probability here doesn't decrease. But if you have a very small energy, you could basically treat this as an infinite potential well, which is the electron in a box thing that I was talking about earlier. So next thing up is the uncertainty principle. What's that's the width of the no. It's the width of the potential barrier. So the wider the potential barrier, the lower the probability of going through. So let's talk about the uncertainty principle. So there's two statements of it. There's obviously the famous one where delta x, delta p is greater or equal to h bar over 2. H bar over 2. And h bar over 2. And essentially, what this means is that the more information you have about the position of an object, the less information you have about its momentum. And the ratio of uncertainties, right? Delta x is uncertainty of position and delta p is uncertainty of momentum, will always be greater than h bar over 2. So so the more you know, let's say you have a particle. Let's say you have a particle here and a wave function, right? And you make it so that it basically looks like this, and then it kind of decays to 0 at other points in space. So, and this is the position. And so you can measure its wavelength because of the wave packet, which I'm not going. Oh, actually, my bad. Let's move. That's for momentum. Let's start with the other thing. So let's say you have a wave that looks like this, right? And you're able to easily measure its wavelength, right? You have a lot of information, you can measure its wavelength. And therefore, you can know its momentum, right? Because you can just apply de Broglie's postulate and just find its momentum. Because you know its wavelength, you can find its momentum. However, since this sine wave is the particle, you don't know where it's in space, because it can be anywhere in space, right? This is an infinite wave, an infinite particle, an infinite wave, and therefore it can be anywhere in space. It could be here, it could be here, you don't know. Now let's say that you add different wavelengths together, so different momentums, right? And you get a wave packet that looks something like this. So now you're localizing the wave, right? Now, it's harder for you to measure the wavelength because it's an average wavelength to start off, so you have some uncertainty in the wavelength. But the position now needs to be somewhere here, and the more wavelengths you add, the more this package becomes like a peak, like that, and therefore you can't measure the wavelength. You don't know the wavelength, but you know the position exactly, and so delta x over delta p is greater than h bar over 2. I'm not going to go over where the h bar over 2 comes from, but you get the idea. And the same thing happens. Actually, you can derive it from one or the other. I'm not going to go into it. I could go into it later, but I don't remember right now the derivation. And I'm not going to spend 20 minutes trying. This is the other statement. So if you know delta x, you will be able to know delta p. The more precision you have on delta x, the lower precision you will have on delta p. So the higher delta x, you increase delta x, you will decrease delta p. And if you decrease delta p, so you get more precision in the actually, hold on. If you decrease delta x, so get more precise in your measurement of position, you will increase your uncertainty momentum. And if you decrease delta p, so get more precise in your measurement of momentum, you will decrease. Yes, exactly. That's exactly it. You can be very precise with the measurement of one. And you won't be, as a matter of fact, if you're super precise, so let's say you manage to measure the position exactly, you will have an error of infinity in the other. You have no idea of the other. If you know one exactly, you don't know where the other is. And this is the other postulate, which is the other way it can be written. And so which basically, if the energy, this is another way of writing it. It can actually be derived from the other one using derivatives. It's not going to be in the exam because it uses calculus to actually derive it. But I could go over derivation once we're done with the session if anyone is interested. And basically what happens here is that let's say we have a pulse in time. So let's say that we have a pulse something like this, right? The more you know the length of the pulse, right? So you know this is a discrete time t, and you measure that, you won't be able to determine the energy. But if you have a very long pulse, of which you don't know the length, you won't be able to determine how long it lasts for. So you will have a high uncertainty in the time, but you will be able to measure the energy of the wave by knowing its wavelength. And that's basically both postulates on the uncertainty principle. Now we move on to 12.2, which is nuclear physics. I'm going to speed up a bit here for those of you who want to leave, because this has been kind of, this has dragged on. Okay, so Rutherford scattering. We start with Rutherford scattering. Give me 1 second. Man, these things are uncomfortable. Okay, so now let's draw a simple schematic of the Geiger-Marsden-Rutherford experiment. So we have a box here. So we have a sheet of gold here. That's a sheet of gold poorly drawn, and then we have a bunch of detectors here. That has to do with the duration, and I'm not going to go over it right now. And it's h over 2, it's h bar over 2, it's h over 4 pi. But actually, I don't think you need to know where the h bar over 2 comes from. But again, if anyone's interested, I can go over it later. I need to actually revise it because I don't remember myself, but it should take a couple of minutes. I have it in my notes. Anyway, so now this emits alpha particles. Right, so this emits alpha particles, and they collide with the atoms in this really sheet-thin of gold. Let's just say it's monatomic, so it only has 1 atom length, 1 atom width, right? And what we observe is that we observe collisions here, and we observe collisions here. But we observe a very small number of collisions on these sides. And Geiger and Marsden and Rutherford went like, wait a second, what the hell? This doesn't make any sense according to our model of the atom, which at that time looked like a plum cake. It was like that, and it had positive and negative charges, something like this. At that point, you wouldn't expect things at the back or such a huge deflection angle. Where was I? Here we go. And so what they did was say, okay, well, this is wrong. This can't be the case. What must happen, since alpha particles are positively charged, you must have a positive nucleus, very small, then a lot of empty space, and then the electrons, since we know the atoms are neutral, must be somewhere around that. And how does this explain the reflection pattern we see? Well, if the alpha particle comes through here, and since the atom is very small, it just flies past, and we detect it at the end of the we detect it here. And so it just flew by free space. And the same thing happens if it flies through here, or here, or here, here, or here. Now, if it gets close to the atom, to the nucleus, the Coulomb repulsion, it doesn't bounce back to the Coulomb repulsion, makes it repel and, for instance, fly back towards the detector. Or if it's coming through here, it will deflect back towards there. So you will measure it over here, right? Or over here. Or you will get deflections here. Right, so you get deflections on these sides of the detector, which can only be explained by this model. They cannot be explained by the plum cake model they had earlier. And so this is basically the Geiger-Marsden experiment. There is not much more to it. I'm going to go a bit more over the maths now, but this is just the theory of it. Then let's say we have an alpha particle that's traveling towards the stationary nucleus. And it will only get up to distance d before being repelled. And at that point, we have energy given by the Coulomb repulsion, which is K, Ce, which is the charge of the nucleus, times 2e, which is the charge of the alpha particle, right? An alpha particle, remember, it's an atom nucleus with 2 positive charges, and the distance d, right? It doesn't get any closer than d. And this will be the kinetic energy the particle has. And then from that, knowing if kinetic energy is large, you can find the atom of the nucleus, or the radius of the nucleus. Because, well, actually, this is just an approximation, but you can actually use this approximation, not a to the 1/3, where a is the number of nucleons. And R naught is given by the, I think it's the atom, or the length of hydrogen atom. I actually don't know if this is an exam. I am looking at a book, but I'm not entirely sure. And so this will be the kinetic energy of your alpha particle, and this will be the radius of the atom. An approximation, obviously. I actually haven't seen it in the exam. Oh, okay, it has been used in the exam. So if they ask for the energy of an alpha particle, use Coulomb repulsion. And then you can find, and so basically what you can store from here, if you know the kinetic energy the particle has, right? They could give you, it has a kinetic energy of, let's say, I don't know, whatever it has. You could solve obviously for d, and then just get the distance of closest approach is going to be KZE times 2e over the kinetic energy. And that's going to be the distance of closest approach to the nucleus. And then this equation is just to make approximation. And then the last thing I think we have to go over Actually, no, nuclear energy levels. I went over that in topic 7, but I could go over it again if for those of you who didn't attend. So, CE is C is the atomic number, I think it's called, or mass number. Not sure. Is it the atomic number? It's the number of protons. Let's say, because I don't remember what the exact designation was. And E is the charge of an electron or a proton. And so Ce is the charge in the nucleus, and 2e is the charge of an alpha particle. Does the equation KZe times 2e over d? Yes, exactly. The equation is this one. There we go. Okay, so last thing, nuclear energy levels. Actually, the second to last thing. So, just as we mentioned, some of you may recall, you can have energy levels in an electron, and you can have energy levels in a nucleus. Basically, and nucleus can become excited as well. So essentially, you would have the exact same thing you had in an electron, same kind of principle. Let's say you have an energy here, which I'm just copying from the internet, but I'm sure in the exam you will be given it. So, but for a hydrogen atom, it is given by minus 13.6 electron volts over n squared, where n is the energy level. And this is, we got this result earlier. But I don't know if this is I don't think what I'm drawing is a nickel nucleus, so this doesn't hold. So you will probably be given the energy levels in the exam. Computing them is not simple and not trivial actually. And here you have the ground state energy, right? Which I'm just going to say is the ground state energy, which I'm just going to call 0. Actually, this is the other way around, but anyway, let's just say this is the ground state energy, and the more energy you have, the more, well, yeah. And let's say these are positive energies, and you have the excitation energy somewhere at the top. And so what happens, right, is you can obviously have atomic transitions, so from here to here, for example, or from here to here, or from, I don't know, here to here. And you will emit gamma radiation, which is actually, I should draw, equivalent to the difference between energy levels, right? So in this case, you will emit 2.158 mega electron volts because you're dropping 2 energy levels. And so your photon will have energy of 2.158 mega electron volts. You could also get excited by a photon. So if you're in your ground state and you absorb 1.332 mega electron volts, you could get excited to n equals 1. So this is n equals 0, n equals 1, n equals 2, n equals 3. And that's, yeah, I mean, that's basically energy levels. There's not much more to say about that. Just remember that the energy of a photon will be given by the difference in energy levels, and that it will be gamma radiation because you're emitting photons and not any other sort of particles. And then the last thing we will be talking about, or actually 2 more things, neutrinos. Basically very small particles. That conserve quantum number, conserve mass in decays. And their existence was postulated because in beta minus decays, or in beta plus decays as well, mass was not seen conserved, or was not observed to be conserved. And so they said, well, there must be a particle that is carrying away that mass that we're missing, that very little mass that we're missing. And there was, and it was the neutrino, which is actually denoted by the letter Greek mu, that looks like this. And there's 3 generations. Actually, this is topic 7, but there's 3 generations of neutrinos. You have the electronic neutrino, the leptonic neutrino, and the tauonic neutrino. Oops. And it depends on what. Actually, that's an antineutrino. This is the notation for a normal neutrino. But yeah, that's basically what the neutrino is. It conserves. It's electrically neutral, and it just serves as conservation for the lepton number and the mass and lepton number in the case. Okay, and lastly, and they were really abundant in the early universe. There is a lot of them in supernovas. It's actually how we detect supernovas some of the time by observing the showers of neutrinos, and they're very, very hard to detect. If you look at the ice cube in Antarctica, that's a big-ass neutrino detector. And they also have very interesting properties, which like oscillations and stuff. And yeah, it's a pretty interesting topic. But I'm not going to go into detail because they're not going to ask you about oscillations of neutrinos in the exam. Okay, so last thing, law of radioactive decay. Very simple thing. Active decay. So we mentioned in topic 7, we mentioned half-lives, but we can also measure radioactive decay, but the law of radioactive decay, which says that the activity decays exponentially, obeying this thing right here, where tau is the time constant, also known as the time for the time taken for activity, to decay to e to the minus 1 of its original value. But you can check this by doing r of tau is equal to r naught e to the minus 1. So right when t is equal to tau, you get that the activity's e to the minus 1 its original value. And then we also define the decay constant, lambda, as 1 over tau. And this is the probability of decay of a nucleus per unit time. And just as a last exercise that I'm going to go over, let's find the relationship between half-life and time constant, which some of you may know by heart, but let's derive it real quick. Let's remember that the definition of the half-life was the time taken for the activity to decay to 1 over 2 of its original value, right? And so let's just plug that into our equation. So we have r at, let's say that, let's denote it by t1/2, right? So we have a notation. This will be equal to r naught times 0.5, that will be 1/2 of the activity, and it will be given by r naught e to the minus t over t to the 1/2. And so this cancels out, and we get that 0.5 is equal to e to the minus t over t to the 1/2. Actually, I made a mistake here. My bad. And forget it. This is wrong. Made a mistake here and made a mistake here. Okay, well, so that's going to be minus t to the 1/2 over tau, and so those cancels out, and we get minus t to the 1/2 over tau. And so let's take natural log of both sides. So natural log of 2 is equal to t to the 1 minus t to the 1/2 over tau. And if we now pass the log to the other side, we get actually this is natural log of 1 over 2, my bad, not 2, 1 over 2, like that. And so we can pass the minus sign to the side, so we get minus ln of 1 over 2, which is equal to ln of 2, right? Because that is we can put the natural log in, we can do that to the minus 1, which is equal to ln of 2, and this will be equal, so we have ln of 2 equal to t to the 1/2 over tau, or ln of 2 or t to the 1/2 over ln of 2 is equal to tau. Actually, no, wait a second. It's ln of 2 divided by multiplied by sides by tau divided by sides by ln of 2. So it's 1 is equal to t to the 1/2 over ln of 2. Yeah, so tau is equal to t to the 1/2 over ln of 2. And so this expression is one that some of you may have seen before, and that's how you derive it. And this is a question they can very well ask you in the exam. And so that's it for the theory of topic 12. Do you want me to go over some papers? This has been a bit longer than I expected. It's been an hour and a half rather than an hour. Would you like me to go? Yeah, wait a second. Yes, what's up? Oh. Oh. I don't know if if you need to derive Half-Life, but okay, I'll go over some questions. I'll go over 5 for 6. Let me just pull up the question bank. Let me just look at the question bank. Bloody hell, I mean, kudos to them for hosting a session for 4 hours. I'd give up before that. Let me just... Okay, let's start with some questions about 12.1. Let's see... Actually... Hold on, I'm gonna leave the call with this computer in a second. I'm gonna stop recording now, and I'll upload 2 recordings, one with exercise and one with this. So I'm just gonna